decision-making team. If you are a consultant, external to your organization, you would give it to whatever team that you're advising. This format here I used or provided to you in an outline. You can follow that same type of structure. Really, the formatting of the white paper is up to you. I like to see creativity. I like to see what comes out of your professional orientation. Okay? So the report is written. The audience is industry practitioners. The length is about 5 to 7 pages. Probably be a little bit longer, but you don't want to be any less than that range. Citation style, your choice. APA is a good choice. Other people use Chicago style. And document format is your discretion. Again, you can use any style that you think is professional. You can convey the information that you want to convey and tell the story about this model that you built. All right, so report format is going to include a title page. Then the second page would be roughly an executive summary. Please don't count the title page as one of your pages of content. I mean, 5 pages, one of them is the title. All right, have the executive summary there. The body is going to be the bulk of your white paper. I gave you a structure to follow. The introduction. Now, the introduction is going to introduce your research question. And essentially, what I ask you to do is talk about the problem. What is start from a problem orientation. Define the problem. Why is it important? Why is it significant within organizations? Why is this a question that you think is valid to be answered at this point in time? Move on to the purpose of your research report. What is your what question specifically are you seeking to answer? That builds upon the problem. Finally, delve into the background of the problem and the opportunity. So I gave you a little bit of guidance there. I said this is where you draw upon the literature that you collected to explain and give shape to the concepts in your research model. You want to make sure that you have these included. So a definition for each of your constructs. So if you're talking about engagement, what does engagement mean? How does engagement play itself out within organizations? What does it look like? What is the nature and history of engagement? Have researchers been looking at this for some time? If so, how long? What are some general findings that they have related to engagement? What are some of the advances or gaps related to this particular idea? Now, you've already done your lit review, and you can pull this information from those particular articles, usually within the first introductory section or in the construct definition section of each article. And I showed you that several weeks ago where you can find those types of things. Move through, talk about the importance of the topic, your objectives, and then finally include your model and diagram. So that's the introduction and research portion. You're going to move into the methodology. I gave you pretty much the standard format. Essentially, what you're going to do is you're going to talk about the fact that you created a questionnaire using valid and pre-existing questions from previous research. And you are going to talk a little bit about your sample demographics. Now, many of you gave your demographics to people who were employed, general employees within organizations, so that's how I would describe my sample. For this class, we did not collect demographic variables, so I didn't worry about gender, I didn't worry about age, I didn't worry about income levels, things of that sort. We didn't need it to show you the basic ideas of how to engage in this process, and we just add a little bit more complexity to it. So I skipped those aspects. So you don't have to talk about those elements. If you see them mentioned in my framework, if you were engaging in this process, you would include a discussion on those things in that area, but it's not going to be present in our submission. All right. Part C, results, is probably going to be the most complicated aspect of your paper, and I've asked you to hold off on worrying about that until we go through what we're going to go through today. It still won't make sense to you right now, but after today, hopefully this will make a lot more sense. And the results section, I asked you to standardize it, and I gave you the standard format, so you don't have to get creative here. The reason I want you to standardize it is because it's going to take you some practice to get used to talking about data analysis results in the most basic format that can be explained to other people. And once you get that basic structure down and you understand it, then you'll get better at explaining how results are impacting the organization that you're working with. So I want you to stick with that format. Okay. In your discussion, recommendations, and conclusions, this is where you get to yield your creativity and talk about your interpretive analysis based on the results that you found. And then, of course, include your bibliography and appendix. The appendix is going to include some data analysis that I will show you how to do today. Okay. So that's the basic structure of the white paper. Hopefully you had a chance to review that before today. Any questions on that? All right, the white paper is due on the 19th, April 19th. That's the final thing. And I'm more than willing to take a look at your white papers if you want to say, hey, what do you think? Am I on target before the 19th? Take a look at it and do some comments on that. Okay, so that's where we're going. That's our ultimate destination. There's only two missing pieces in order to get you there. You've done the lit review, you've done the methodology, which was a constructive questionnaire. The missing piece is the data analysis and the results. Okay? So there are two assignments that are going to that you're going to work on over the next couple of weeks that will help you in that respect. I'm going to introduce those two assignments to you. They're in a section called Data Analysis Assignments. One is called Data Analysis Part 1. That consists solely of definitions. The second is Data Analysis Part 2. That is a step-by-step rubric of how you're going to engage in your data analysis. And we're actually going to be working through that assignment today. So let me introduce Part 1 to you. Data Analysis 1 contains 10 sections, and all I'm asking you to do is to tell me your understanding of each of these terms. These terms won't necessarily make it into your white paper, but having an understanding of these concepts is important for you to be able to explain what's going on in this process that you're engaged in. So tell me what a population is, what is a sample, what is bias when it comes to decision making and research. Talk about descriptive analysis, and specifically mean variance and standard deviation. Now, I said in my instructions, in all cases, explain the main term, and where applicable, also include an explanation of the subterm. So here, I want you to tell me what descriptive analysis is, and then I also want you to define these subterms, mean, variance, standard deviation. Tell me what levels of measurement are broadly, and then tell me what the 4 levels of measurement are in detail. I want you to talk about hypotheses. I want you to talk about significance level, bivariate analysis, which is the primary analysis that we're going to be doing in this class, define correlation and some subterms associated with that, and regression. Regression is the form, specific form of bivariate analysis. I want you to go into more detail related to that. So not real deep there. Should probably take you maybe, I don't know, a couple hours to dig into this and get that done. But that's a great foundation for you. The next assignment, which is going to be more complex and should take you more time, I really want you to get your hands on it before next week, because if you realize you need help, come to class next week. It's not a scheduled class, but I'll be here. Come here next week, and I'll help guide you, answer questions, figure out what troubles you're running into so that you can work through this analysis. Essentially, this is a 14-plus step process. Where you're going to prepare your data, you're going to do some brief descriptive analysis, you're going to check your scales, collapse your scales, and then test your hypotheses. Okay? So, conceptually not that complex, but in practice it's going to take a little bit of instruction to show you how to do it. And you're going to need to have some familiarity with your data in order to be able to do this effectively. So we'll spend a lot of time working on that today. So that's our work map. That's where we're going. Okay. Now let me introduce some concepts to you before I get into the PowerPoint. All right. This should look very familiar. This is the general model framework that we were following all semester. Okay? Does anybody know that? It's related to hypothesis. Yeah, just warm up, huh? Okay. So we have the abstract level. What level's now here? Empirical level. Okay. When we're talking about relationships at the abstract level, what do we call those? Constructs? Yeah, these are constructs, but when we're talking about the relationship, it's proposals. Yes, or propositions. Yep. Okay, so those are propositions. These are constructs. Okay. We operationalize our constructs down to the empirical level. And when we come down to the empirical level, when we're talking about relationships, we don't call them propositions. What do we call them? Hypotheses, exactly. So this would be P1 at the conceptual level, hypothesis 1 at the empirical level. And they're no longer called constructs, but they're called variables. And you all went through this process. You said, engagement is my construct, it is my idea. And then you went out and you found a question, said, measured how you would assess somebody's engagement through a questionnaire. And those questionnaire responses are going to allow us to essentially go from the abstract level, operationalize it down to the empirical level. That allows us to test our hypothesis through measurement. Okay. Now here's the new concepts that I want to introduce to you related to hypothesis testing. When we enter the variable level, we are now empirical. We can start using statistical terms to describe the relationship. And the most common statistical labeling of variables are X and Y. Okay, you've seen this before, this is not good. X is known as an independent variable, or IV. What that means is the X variable is not dependent upon anything to move. X can be high, X can be low. Okay? Y is known as a dependent variable, or DV. And what that means is that Y is dependent, or this variable is dependent upon the motion that is occurring with the independent variable. Okay. So as X moves, Y is going to move as a result. When X is high, Y might be high. When X is low, Y might be low. Okay? That's known as a correlated or correlated relationship. Everybody follow me? All right. When we're looking at a model, it's important to note that we examine each relationship independently. So this relationship would be one hypothesis, and we would examine this relationship regardless of anything else that's going on in this model. The second relationship down here might be hypothesis 2, and we would examine this relationship independent of anything else that's happening in our model. Okay. So as we're testing our relationships, we focus on only two variables at one time. When we're focusing on two variables, the first variable, or the precursor, is the independent variable, and it is influencing the second variable, which is the dependent variable. So hypothesis 1 is easy. I showed you X here and Y there. Well, let's look at hypothesis 2. What would this variable be? That's an X. And this is a Y. Alright, pretty simple. Alright, now let's look at hypothesis 3. What would this variable be? Right. Okay, so that's something that tends to confuse students. And one analogy analysis, a variable might be a dependent variable. In a subsequent analysis, this same variable might be an independent variable. Okay? So the labeling or nature of the variable, whether it's independent or dependent, is subject only to the specific analysis that you are engaging in at that point in time. So sometimes this will be a dependent variable, but in other analysis, this will be an independent variable. Okay, everybody capturing that? And then we can systematically go through and test the relationship of each variable to see if there is in fact a significant relationship. In other words, these variables hang together enough such that motion in one is resulting in motion in the other. Okay, let me pause. Any questions on that? Pretty simple stuff. Right. So you start doing it, that's like, what in the world is going on here? Okay. Alright. Now, I'm going to ratchet up the complexity just a little bit. Any relationship can be described by a graph. Y'all remember that? Back in high school, middle school even? One thing that really confuses students is which axis represents which piece of data. So I have a little trick that I use, and I'm going to share it with you. Essentially, this is alpha sequence X, Y, Z, so we know X comes before Y. And I think about the graph like building a house. If I'm building a house, the first thing I'm going to lay is the foundation. Right? And so the first line of my house is simply the first alphabet letter that comes in the sequence, which is X. Then after my foundation is done, I'm going to build the walls, and that is my y-axis. Okay? So if you ever get confused as to which axis is the x-axis or y-axis, very simple genetic, be able to remember that. Okay, so X and Y. Alright, now let's get a little deep. So I'm going to label X satisfaction, and Y is going to be engagement. Okay. And I wanted to understand what the relationship between satisfaction and engagement is, so I gave people a survey. And I asked them 3 questions related to satisfaction, and then I averaged those 3 questions together, and I came subject A, subject B, subject C. Subject A said they were 1 level of satisfaction, and their engagement was level 1. The subject B's average satisfaction was 2, and their engagement was 2. And finally, subject 3's satisfaction was 3, and when their satisfaction was 3, their engagement level was actually 3 as well. So if I plot this out, which axis represents satisfaction? The horizontal? Alright, good. And engagement represents the vertical axis. Vertical axis is Y, horizontal axis is X. Okay. And so I can plot this out very easily. When my satisfaction was 1, my engagement was 1. Plot that. When my satisfaction was 2, my engagement was 2. I can plot that. And when my satisfaction was 3, my engagement was 3. I can plot that. Very simple. And in plotting these relationships, I can actually draw a line where I show that the relationship is linear. Now, there's a few things that I can learn from looking at this relationship. The first thing I can learn is that the relationship is positive. It is a positive relationship. And what that means, what a positive relationship means, is that when one variable increases, the other variable increases in the same direction. It also means that when a variable decreases, the other variable decreases in the same direction. So we can see that here. So when my variable increased, when satisfaction increases, what happens to engagement? It increases as well. When satisfaction decreases, what happens to engagement? It decreases as well. So that is a positive relationship. A negative relationship looks different. A negative relationship looks like this. Okay? So as my x variable is increasing, increasing, my y variable is decreasing. That's a negative relationship. Conversely, when my x variable is decreasing, what's happening to my y variable? It's increasing. Okay, so the lower my x, if my x is 1, my y is 4. When my x is 2, my y is 3, and so on. Okay, so that's a negative relationship. This is going to be important to note when you're making your analysis, because positive relationships mean that your variables are moving together. Negative relationships mean that your variables are moving opposite one another. So conceptually, you can kind of tell what direction you expect something will be in. So for example, satisfaction and turnover. What do you expect that relationship to be, positive or negative? Negative, okay. How about salary and satisfaction? Yeah, positive, I would expect that to be. So you kind of can have a general idea of what you expect your variables, the direction or nature of your variables to move in, based upon the conceptual nature of your hypothesis. Okay? So that's positive relationship, negative relationship. Now, let's talk a little bit deeper in relation to this. Now, when you think about a line, you remember the equation rise over run. And what does rise over run represent? The slope, exactly. Okay. All right, so let's look at this. So for satisfaction, my rise is 1 and my run is 1. If I go from this one to 3, again, my rise is 1 and my run is 1. So that indicates my slope is 1. Okay. The slope of a line also represents the correlation or co-relationship of the variables represented by that line. And correlation is a statistic that we're going to be using in depth as a part of our analysis. So when you're dealing with a bivariate, and each of those variables are on the same scale, which is the case with many of our analyses, the correlation is going to represent the slope of the line. Okay. Sometimes, if a slope is less steep, the correlation is going to be less than 1. Okay. If a slope is negative, the correlation is going to be a negative number as well. So if the relationship is negative, the correlation is going to be negative as well. Correlation ranges from positive 1 to negative 1. It's going to fall within that range. What does the correlation of 0 mean? No relationship. There's no relationship at all. Okay? So if you're thinking about a correlation, a positive 1 correlation is a perfectly positive relationship, or a 45-degree upward sloping line. A negative correlation, or a correlation of negative 1, is a perfect negative relationship, or a 45 degrees downward sloping line. All right, everybody following that? Okay, good. So what we're going to do in our data analysis is essentially run equations that plots the line of our relationship. It's going to look at our independent variable and our dependent variable. And it's going to plot the relationship or pairings of each of those observations and then determine if in fact it's a linear relationship that displays a significant interaction with the two variables together. Okay. Pause. Any questions with that? Good. Either I'm doing a great job or you all are messing with me. So yeah, we're going to make pretend we know what's going on. Okay. Before I get into PowerPoint, one last concept that I want to explain to you. And So let's say, for example, we know our relationship is a positive correlation, a +1 correlation, and we're trying to manage engagement with our employees, and we know that we can control employee satisfaction through doing various different interventions. Maybe we can increase their pay with bonuses, maybe we can increase the nature of their job, etc. Is it possible for me to, if employee satisfaction is 1, and I'm trying to drive their satisfaction higher, can I accurately state that for every level of satisfaction that we gain, we know how much engagement we can expect to gain as a result of that gain in satisfaction? And looking at it, once we plot our linear line and we understand the nature of our relationship, can we make projections based upon a gain in our independent variable?
Yes.
Yeah, we can. I mean, once we have the line fixed, any level of satisfaction can give us an expected level of engagement. Okay? So if our organization has overwhelmingly low satisfaction, and we understand the linear relationship between satisfaction and engagement, we know that every increase in satisfaction is going to yield a representative increase in engagement. And in this case, the increase is going to be a 1-for-1 relationship. Okay? Now, not all relationships are going to be that clean. Of course, some are going to be a little bit less. All right, so that is the explaining and predicting aspect of science. So let me get into the PowerPoint now to delve a little bit into some deeper concepts. This is all going to come from chapter 23. So if you want to go to the notes, that's going to be here for you. I'm going to go fairly quickly through this. I just want to make sure that everybody has at least read. If you have not read chapter 23 yet, I want to give you a quick overview of some of these concepts. Okay? So far I've been describing to you the association of two variables together, x and y. Statistically, there are a few different measures of association, and the book outlines several. It talks about chi-square. We're not going to use chi-square. We're going to use correlation, which I just explained to you, and regression. I have not introduced to you the regression line just yet, but when I do, it shouldn't be that difficult for you. Well, actually, let me do that now. Does anybody remember what the equation of a line is? Y equals mx plus b. Okay, so we're going to use a little bit different symbology with this, but let's just explain what these letters are. What is y in what we're talking about right now? It's the dependent variable. What is x? Independent variable. So right now we are saying that our dependent variable is a function of something going on with our independent variable. Well, let's see what's going on here. What does this m represent? Yes, say it louder, I heard it. Slope, yes, exactly. The m represents the slope. Anybody know what the b represents?
The y-intercept.
It's the y-intercept, exactly. It's the constant. Alright, so that is the equation of the line, and what we're talking about is representing a relationship between two variables linearly. So as we move into this, we're going to start pulling or understanding pieces of the linear equation. Y equals slope times the x variable plus the constant, or the y-intercept. Alright, so our statistical analysis is going to help us understand primarily two things. Our slope and the intercept. And in knowing our slope and intercept, we can very easily define the relationship between our independent variable x and our dependent variable y. Alright, so that's what regression is. Regression is using the linear equation to understand the relationship between the two variables. Okay, now, there are different types of data, 4 different data types that you can essentially collect. Many organizations make the mistake because they collect data in the wrong realm or wrong type of measurement. A lot of organizations, when I see their survey, their data is in the nominal or ordinal level. And essentially what nominal data is just names or categorization. So examples of nominal would be gender. You could have different categories for gender. Nominal would also be like, department, what department you're in. What is your ethnicity would be a nominal aspect of data. Okay? You can run statistical analysis on nominal data, but you cannot run linear analysis with nominal data. Okay? So linear analysis is the most robust data analysis that we can utilize. So we're going to avoid nominal data, and that's why I really didn't focus on demographic data like gender and things of that aspect in your data set. The next type of data is ordinal data. It's a step up from nominal. It gives us a little bit more detail, but it doesn't tell us a lot of information. Ordinal data would be an example of first, second, third. Now with ordinal data, we can rank things, whereas in nominal data, we cannot even rank. But our ranking doesn't really mean anything. So if you're talking about a race, and you want to know the statistical performance of the runners in the race, it's neat to know who came in first, second, or third, but then we can't answer any subsequent questions. We don't know what the distance was between first and second place. We don't know what the gap is. We don't know how close they were, and so on. We have no idea with ordinal data what the statistical relationship is between the rankings of information. Okay? So when you're working with data analysis, you want to always try to work with the richest type of data, and that is interval or ratio data. Interval or ratio. Now we use Likert scales in our questions, and Likert has gone through a long history in psychometrics to where essentially researchers have determined that the gap between items on Likert scale analysis is discrete enough that we can call it interval data. Okay, it's discrete enough that it falls within the interval category. And ratio data is just taking interval data and standardizing it. Okay, so a ratio would be like miles, which is interval. We can have 1 mile, 2 mile, 3 mile, 4 mile, 5 miles. That's an interval. And ratio is miles per hour. It's taking an interval and standardizing it through some other mechanism. So miles per hour would be an interval. Salary per year would be another example of an interval. Okay. Or, I'm sorry, ratio. So interval and ratio, we kind of use those together when we look for this type of data to run our statistical analysis. In your questionnaires, we focus on interval data. And we're not really going to be using ratio. Maybe 1 or 2 groups have some ratio questions in there, but we'll see as we get along with that. All right. Okay, so once we have our interval, we see that we can actually use the statistical analysis of regression and correlation to help us describe the relationship with 2 variables. Whereas on the lower level types, we have to use different types of tests. We can't utilize regression analysis. We're using a lot of power in the type of analysis that we have to do within organizations. You can explain, but you cannot predict. But with regression, you can both explain and predict. All right, I've used the term correlation before. A statistical measure of covariation or association between 2 variables. When 2 variables are moving together, there's going to be a phenomenon called variance. So let me explain what that is. you're going to have lots of people with lots of observations. So your X's are going to range from 1 to 5 on a 5-point Likert scale, and your Y's are going to range from 1 to 5 as well. And there's going to be cross, depending on if it's a positive relationship, I'll just show a positive relationship. There's going to be a whole lot of cross observations associated with this data. Okay? The fluctuation in observations, the way that X fluctuates, some people are going to be 1s, some people are going to be 5s. The way that Y fluctuates, some people are going to be 1s, some people are going to be 5s. And then the fluctuation of the matchings, some ones are going to correspond with 1s, other ones might correspond with 2s in the dependent variable. You might have some instances where 1s correspond with 3s in the dependent variable. You're going to get a lot of these cross correspondence relationships. This static in here, that's called variance. Okay? Essentially, your variables are varying. That's why we call them variables. Sometimes they're high, sometimes they're low. Sometimes they're high and low together. Sometimes they're high and low apart. Okay? All of that, all of those nuances, all of the ways in which they differ from one another is called generally variance. Okay? So that's the conceptual idea of variance. We want to be able to explain that variance. We want to be able to say, okay, we have an understanding of this independent variable and this dependent variable, and we understand the variance in the dependent variable based upon fluctuations in the independent variable. In fact, with the regression analysis, based upon our coefficient of determination, which I'll introduce you what that is, we'll actually be able to explain percentages of variances in our dependent variable. So we can get to the point where we can say, your satisfaction or your engagement is varying quite a bit in the organization, but we can explain 70% of the variation in your organization's engagement by understanding satisfaction. So in other words, satisfaction is accounting for almost 3/4 of the variation of engagement of employees within the organization. That's a really neat fact of how we communicate. So R is a correlation coefficient. It ranges from +1 to -1. I've already explained to you what that means. No relationship is a correlation of 0. Here's some examples of positive correlation up here and negative correlation down here. Now, in my introduction, I showed you a perfect positive correlation, which is a 45-degree angle, a perfect negative correlation, which is a 45-degree negative or downward angle. But in real life, our data is not going to look like that. Our data is going to have lots of different observations. So when X is 1 here, Y is going to be, 2.5. And when X is, 0.9, in this observation, Y is 3. It's going to be all over the place. Sometimes the groupings are going to be very loose, and that suggests a weaker correlation. Sometimes the groupings are going to be tight. That suggests a higher correlation. Okay? And remember, I like to say correlate because it's easier to understand. This is how the variables are correlating to each other. Here's a negative. Here's no correlation. It's just basically all over the map. Here's a downward sloping grouping. This is moderate negative correlation, and actually perfect negative correlation. Questions? Patterns? All right. Okay. Okay, one thing to note, and you'll hear this a lot, my kids like to throw this around all the time. Dad, correlation does not equal causation. Yes, I know that. Okay. Oftentimes, though, items that are correlated with one another do have causal mechanisms that are playing together. All right, but the way that we justify that is we start with the foundation of theory. So that's why every time we're in this process, the very first thing that we do before we go around the circle is we start with theory. So theoretically, we know that satisfaction is related to engagement. And so if I show a correlation between satisfaction and engagement, I can actually make a determination that satisfaction is causing or driving the relationship with engagement. Okay? Now, you can't do that with everything. I think that at the very beginning of the semester, we look at ice cream sales in the summertime and violence. Okay? So just because ice cream sales is related to violence doesn't mean that they are actually causal in nature. They're just correlated. So theory doesn't support that relationship. Again, roosters do not cause the sun to rise. There's a correlationship there, but not causation. Always stick with theory to help explain the causal relationship. Okay, here's the coefficient determination, which I promised to introduce to you. And all it is our slope squared, or our R squared, our correlation squared. Okay. Essentially, the way that's calculated is that we take the total variance that is observed in the dependent variable, and the top is the total variance explained by the independent variable. Okay. So the variance explained divided by total variance is going to give us a portion of total variance explained. You can see that by the visual representation here. So going back to our relationship between X and Y, which is satisfaction and engagement. Once I determine my correlation, I can easily calculate my R squared, although the program is going to do that for us. And I know that my R squared is going to represent, I'm just going to say 0.78 here. My R squared is going to be 0.78, and that represents 78% of the variance in engagement is explained by understanding satisfaction. So once I understand one variable, I can explain why the other variable is fluctuating. Okay. This gets really neat when you get into your model, because you see here, when you get to your problem, you're actually going to evaluate two relationships associated with your problem. So let's say that this one is engagement, this is satisfaction, and let's say that this is, I don't know, let's say your perceived or support. Once you understand the relationship, the R here and the R here, we can easily calculate the R squared for each relationship, and you might find that 70% of employee engagement is explained by satisfaction, and 15% of employee engagement is explained by perceived organizational support. And so combined, we have over 85% of the variation in engagement is explained by these two variables. Now, it's not total explanation. It means that there's other variables that are also impacting engagement, but we have a great amount of explanatory power with understanding these two aspects in relation to engagement. All right. A correlation matrix is simply a table that expresses all the correlations available in your model. I'll show you how to build that. I want to introduce the term statistical significance. This is the threshold that we utilize to determine that the relationship is not occurring by chance. We usually use a 5% threshold or 95% confidence. Okay? So we look for significance to be less than 0.05. And we're going to be looking at the P, or probability value, to make that determination. If the probability value is less than 0.05, we say that there is a significant relationship and our hypothesis is supported. If P is greater than 0.05, we say that we do not have enough information to support this relationship as it stands. In other words, our data is such that we can't rule out happenstance or chance in the findings that we're viewing with this relationship. I'm not going to worry about type 1, type 2 error and those types of things that are a little bit deeper into statistics because as HR professionals, you're not really going to be using those types of terms when you're presenting these to your stakeholders as you go through this process. But if you follow the method that I've been showing you all semester long, you're going to minimize the likelihood that you're going to have errors in your results. So you're going to minimize finding false positive results or rejecting relationships that otherwise would stand in the future. Okay, here's an example of a correlation matrix. Let me just show you how to read this since I have it up. Essentially, a correlation matrix are the variables listed on both sides. So you have vertically the variables listed, and then you have horizontally the same exact variables listed. So here's performance, it's coded S, I'm not sure why, but performance to performance has a relationship or correlation of 1. And you'll see that the diagonal all the way around, all the way down, is 1 because that represents each variable correlated with itself. But here we have something really neat. We can actually view now job satisfaction or performance in relation to job satisfaction. The relationship is 0.45. Here's a strong one, 0.61, self-esteem with satisfaction. Here's some negative relationships. So a correlation table shows us our relationships statistically in one chart. Very simple way of putting together your relationships. Okay, finally, the regression. This is the equation that we're going to be using. Here's the symbology that we use in the business. We have our x and y, of course, which is the same. For our constant, we're going to use the alpha. And for our slope, we're going to use beta. Okay, so x, y, alpha, beta. Very simple stuff. When we run our regression analysis, you're going to be understanding what the intercept is and the beta in relation to the x and y. Okay. One thing I want to point out, and if you can, jot this in your notes because you can make this mistake. The beta that we're going to look at, our analysis is going to give us two betas. It's going to give us an unstandardized correlation coefficient, and it's going to give us a standardized correlation coefficient. For our class, we're using the unstandardized correlation coefficient. Unstandardized is best when you have discrete scales that are fairly consistent and you can describe what the scales mean. So we're using Likert scales. And we know that 1 is strongly agree, 5 is strongly disagree. When we find our slope, we want to be able to represent that slope in the same scale that we used in our questionnaire. Sometimes researchers like to use the standardized, and essentially what they're doing is they're converting the scales into standard deviations, and then if you do that, you begin explaining the relationship in standard deviations as opposed to units. And that gets confusing, and it's easier with business practitioners to stick with unit descriptions as opposed to standard deviation descriptions. So that is what is up here. The beta is indicative of strength and direction relationship. It's this side here. The raw regression or unstandardized beta coefficient is what we're using in this class. We're not going to be using the standardized beta coefficient because it's basically you're using a constant scale and you convert your discussion to standard deviations as opposed to units. Okay. Plus, we want to explain and predict, and forecasting is most often utilized with the unstandardized or raw regression. Okay, here's a linear line. Let's revisit a few terms that I introduced to you. What do we have here? X-axis, otherwise known as independent variable. Here we have Y-axis, also known as dependent variable. Okay. How do we get this line here? Rise when we run, but how do we get our initial plot points? Yeah, we're looking at our data. For every value of X, we have a corresponding value of Y. We just plot those on the graph. And so we see the plot points here. Okay? Now, you notice that the line doesn't necessarily go directly through the plot points. Why do you think that is? What do you think's going on there?
Best fit line.
This is the best fit line, exactly. We call this, well, yes, you guys are getting it, I'm so happy. Yes, this is the best fit line. Essentially, it's the line that minimizes the variance in between observations, okay? So we're minimizing the deviation from the center of the line here. And so we use statistical software to help us draw that line. All right, we have here the y-intercept, otherwise known as the alpha. Okay? The slope or rise over arc is going to be the beta, or the raw parameter estimate. Chapter 23 is really going to be your go-to chapter for getting your head around this stuff. If, outside of this class, to say, okay, help me to refresh our understanding exactly what's going on. All right. Okay, here's something interesting I wanted to show you. Once we have our regression line, again, I told you we can make predictions. These predictions are not going to be perfect, but they're going to be in the general ballpark vicinity. So, for example, when blood pressure is 160, based on our regression line, we can expect sales, is this blood pressure, or whatever BP is. BP related to sales. If my blood pressure is going through the roof, sales better increase, right? All right, so when my blood pressure is 160, my sales should be right about here, okay? But the actual observation is a little bit above that. Okay, so that indicates that it's not perfect, but it does get us into the ballpark once we get the regression line. All right. Here's an example of data output, and I'm going to show you a different program. This is SPSS. I'm going to use a different program because SPSS is expensive, and students oftentimes don't have access to it unless you use the computer facilities here at EMU. So you're free to use SPSS. I'm going to give you an alternative that you can download for free. It's going to do the same thing. Okay? But here's SPSS output. We see here that we have a few different things. First of all, the way SPSS works is that it's a little bit different. It tells you your dependent variable. Here's sales. Here's permits. Okay. That's what BP might mean, permits.
Building permits.
What's that?
Building permits.
Building permits. There it is. I'm not actually reading the detail. So here's your DP, your DV, your sales. Your IV is permits. Okay. Here's your model F statistic. We're not going to go too deep into that, but really what you're going to be looking at is the significance of your model. And the significance is the p-value, or probability that this model is occurring by chance. And in this case, what's the probability? Zero. Pretty much zero. So would this model be significant? Let's see. How many people say, yes, this is a significant model? 3. How many people say, no, the p-value is like 0, this is not significant? Okay? We're learning here. We're just sharing and learning. Okay? All right, coming back to this, what we're looking for, significance, is we're looking for a less than 5% chance, of randomness. Okay? So the lower the probability of randomness, the better it is to help us determine the significance of the relationship. Okay? So when p-value is low, significance is what? High. Yes, it's an inverse relationship. So we like low p-values. So p-value of 0.000 is beautiful, because that means there's virtually no chance that this relationship is happening randomly. And in fact, we can support a relationship occurring between permits and sales. Okay? We see it again here, significance 0.000. All right? And here is our beta, 0.546. That is our slope. 0.546. So for every one increase in our independent variable, how how much is our dependent variable increasing? Yeah, by about half. Alright. Okay. Our R squared, or the amount of variance that is able to be explained by understanding our business permits on sales, is close to 88%. That's really robust. Okay, 88%. Okay, so here's our slope, here's our significance level, and this is our R squared. Those are numbers that you're going to want to draw from when we're doing homework. So let me get to that real quick. In this assignment, when I'm asking you to test your hypotheses, I'm asking you to name your dependent variable, to name your independent variable, and I'm asking you to run your significance, or your regression rather. I'm asking you to record the significance level of your model, what the slope is, and what the variance explained is. Those are the three numbers that I want you to capture. Okay? And you're going to do that for each of your five hypotheses. I built three of those. You can copy and paste for the rest of them. All right. Revisiting this line, you've seen this already. Another example of how sometimes we can make a prediction. When x is 100, we expect y to be falling right on this line. But you see that sometimes there's a little bit of variation around there. That's okay. If there's too much variation, if the line is not a good predictor, then the model's not going to be significant. You'll have an insignificant model. All right. So just to put it into practice, let's say that I am looking at a relationship between size and weight. My hypothesis is perceptions that a model is overweight is negatively related to perceptions of attractiveness. What's my independent variable in this hypothesis? Which is it?
Weight.
Yep, perception of weight. Okay. And my DV? Perception of attractiveness. So when I input this into my regression analysis, I want to make sure I have those in the right order. It can be tested with simple regression. This is very similar to every hypothesis that you have in your models, and regression is going to be able to either support or fail to support the hypothesis. Right. So when you're testing hypothesis and using regression, essentially you're going to be looking at what is the direction of the line? Is it a positive relationship, negative relationship? What is the strength of the slope? What is the significance of the model, the p-value? And how much variance is explained by understanding one variable in relation to the other? All right, that's it. That is statistics in a nutshell. Do we have any questions on that?
So back to one of these regression lines.
Yeah.
Where is our R squared in that line?
R squared would not be on the regression line.
But it's the, I think if our R squared is 0.875 on the permit example. I mean, 87.5% of the dots are close to that line, or how do you?
No, what it means is of the variability of the dots from the mean, our independent variable explains 87% of that variance. Okay. So our dependent variable is going to be bouncing all over the place, and you want to understand the fluctuation. And so you're saying the R squared says this is of all this fluctuation that's occurring, my independent variable is explaining 80% of that fluctuation. This becomes really useful when you're trying to change outcomes within organizations, like increase sales, and sales is fluctuating based upon numbers of permits pulled. And that's like, okay, well, if we really want to drive sales, let's focus on pulling permits. Now, what's really neat is that sometimes organizations have two different ideas, and that's why I generally had two different factors to try to solve the problem.
Sometimes organizations have limited resources and they can only pursue one course of intervention at a time. And so by testing the interventions separately, you can actually say, engaging in this intervention is actually going to be more effective than engaging in this intervention because this explains 70% of the variance of engagement, whereas this only explains 15% of the variance of engagement. But without this type of analysis, an organization might say, well, I bet we can increase perceived organizational support, let's throw our money at that. Okay? Not necessarily a bad idea, but not the most effective idea if you have limited resources and can only pursue one intervention at a time.
Interesting, of those two Ys, one's 70%, the other's 15%. What if there's a Y that would blow both the amount of water that you just didn't test for?
There's another one?
If there's a third one that you
Yeah.
didn't test for.
That can happen. Yep, for sure can. In fact, you might find in your analysis that both of your explanations are low. This might be 15%, this might be 15%. It's like, well, what else is going on here?
So yeah, that's not.
Back to the drawing board. Okay, back to thinking about what other aspects. And that's why at the front end, brainstorming is so important, where you're trying to brainstorm all the potential causes, and then you're kind of engaging in a root cause analysis where you're building out the model. And you say, we think that this is the best case explanation of what it is that's going on in the organization. Let's go ahead and try to test this phenomenon. Okay. Any questions? Others? All right, let's take a 10-minute break, and we'll come back and do some analysis. You might actually work along with me on your laptop as I go. All right, so, and excuse my voice, I recovered from a cold. I actually did not have a voice this past week, so this is me actually improved. All the data sets are posted online. These data sets have been, well, I'll show you what they are real quick. Each group has their own data set, so you can access the data set associated with your group. Please know that all of the assignments from this point forward are individual. So I want everybody to be providing their own definitions for part 1, that's homework, and I want you to do your own analysis for part 2 of this, which is what I'm going to show you now. So I'm going to show you engagement data. Just click on this, download it, and I've pre-downloaded it here. The engagement group will benefit from me showing you how to do this. This is your raw data. As you see, it's really just a whole bunch of numbers. Okay, it looks like the matrix. What I did here is I coded the construct and the question number. So for engagement, you had 9 questions, or the final survey had 9 questions for engagement. This is question 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I left, in the raw data set, I left the questions in row 2 of the analysis. So you can look at the question and say, okay, that's exactly what this question is answering. And I would say you want to make sure that you keep this data set, the integrity of it, so that you have access to those questions in one file, and then you're going to create another file where you delete that row, because when you import it into your statistical analysis, it will throw your analysis off, having that row 2 in there. So have one file with the row, have another file without it. Okay. So let's start with the homework. So step 1 is simply count the number of responses that you had. Some groups had more responses than others. This group, engagement, had 60 or 59 responses. Okay, so that's your, actually it's 58. You delete row 1 and 2. So that would be the number of responses that this group had. Export your data in Microsoft Excel. I did that for you. Rename your fields. I did that for you as well. You can go in here and change the fields if you want to change it into something more intuitive for you. I would just say try to keep the fields short so that when you import it into the statistics program, it's easier to manage. I'll show you what that looks like. So as you see, this individual here individual number 1, which is in row 3, gave their answers to the engagement questions, to the WCON. Was that work conditions? Where's my engagement group? All right, so work conditions questions. There's 3 of those. Work-life balance questions, culture questions, and satisfaction questions, and turnover questions. All right. Now, in a lot of cases, I revised your survey just a little bit to condense it down so people can take it in a shorter amount of time, and you don't have a whole lot of people cleaning the questions up. Okay, so going back to this, the data's exported, the fields are renamed. Okay, update your key. What I recommend, and it's not going to be too difficult here because you only have a limited number of constructs, but I recommend that people kind of have a key that tells them that ENG is engagement, WCON is work conditions. Just have some sort of reference so that you don't get confused when you're engaging in your work. And also, as a part of your key, I also recommend that you orient your questions. So you know that low numbers represents agreement, and high numbers represents disagreement. Okay, so in addition to your labels, you want to make sure that you understand your polarity of your scales. And this is pretty standard. It does get a little difficult in interpretation because usually higher numbers means higher level of agreement, but we'll just reverse that. You know, the closer to 1 something is, the more agreement you have, and vice versa. The closer to 5 you get. Okay? So I recommend that you create a key for your own reference. All right, step 5, highlight reverse questions. This is a very important step. In order to highlight reverse questions, you just have to look at your questions to determine, are any of these questions in reverse polarity from what I would expect them to be. So I'll just walk through this with engagement. I am inspired to meet my goals at work. Let's make pretend I totally agree, I'm totally engaged. I would answer a 1 on that. Okay, so 1 is going to be my total agreement. Question 2. Our company provides a culture in which I can thrive. Am I going to answer 1 on that? Yes, so that's 5. The mission and purpose of work makes me feel important. 1. Good. I feel valued at work by my coworkers. 1. I feel involved in key decisions. 1. I have the resources to succeed at my job. 1. I feel that my position contributes to the team. 1. I am uninspired to take on new projects outside of my set job tasks. 5. You see how that happened? If I'm totally engaged and I'm making pretend I'm like the uber engaged employee and I'm taking this questionnaire, would I answer 1 on this question? Okay, so that lets me know that this question is reverse scored. So you have to make a note of that. And the way that I do that is I say MR needs reversing. Needs reversing. Okay? And then finally, number 9, I feel transient at this company or role. Okay, that needs reversing as well. Okay. So when you go through all of your questions, do that for each construct. Okay. Set your polarity for total agreement, and then answer each question as if you were the Uber agreement employee. Any question that you would answer a 5 for needs to be reversed. It's the opposite polarity. Okay? So go through in your homework. Step 5 is to highlight reverse items, which is what I'm showing you how to do there. Oh, I said, and maybe that doesn't. Okay, step 6. Physically reverse your items. Now this is easiest done in Excel with find and replace. And what I do is I'll introduce a new column. I'll call this engagement question 8 reversed. Okay. can write an if-then statement, that takes a little bit of time. But you can also do it physically, so for every 4, make it into a 2, and so forth. But what I'm going to do is I'm just going to copy and paste, then I'm going to Control F, which is find and replace. And I'm going to find all 1s and replace them with 5s and replace all. It's going to make 4 replacements in this highlighted data set. I'm then going to find all 2s and replace them with 4s, replace all. That's 9 replacements. 3s, I don't have to replace. 4s, I'm going to replace with 2s, replace all, 29 of those. And 5s, I'm going to replace with 1s, replace all, make it 20 of those.
So if people would mess it up, though, like in regards to after you do the 2s to 4s, that won't change it back from 4s to 2s?
Oh, good question. Did I do that? Actually, I may have. Ah, shoot.
Well, if you copied the thing over, you can see what the
It was 4, 2, 3, 1s, 5 1s, 4s, 2s.
Oh, what 2 is it?
you would have.
5 became 1s. Looks like it worked.
No.
4s.
2's a 2.
Oh, 2s are 2s. Yep. That did reverse now. Good catch. Thank you. That did not work the way I wanted it to. So, won't do that. All of my research I've ever published is invalid. Actually, I usually do this in SPSS. They have a function that you can write in SPSS and it does it for you. But I'm trying to, they want us to use more Excel, and obviously I'm not the one to be showing you how to do that. So you can physically go through and do this, 5s, 3s, and so on and so forth. Maybe I'll just go through and do that. So all my 4s are 2s, 1, 2, 2, 1. Doesn't take long doing it like this.
It's got to be a function. There has to be a
You could write it in.
You can write an if-then function if you want to. I don't want to get into all of that at the moment. Okay, I just want to get through, reverse this. We're going to go through this process. Oh, what a great catch. Almost done. Okay, so that's how you go through and reverse. Okay, if you're fancy, you can write the if-then function, and you want to do that for all of your reverse questions. Okay. Save copies of your data. Once you go through that, I like to keep multiple copies, especially when I'm playing around with the data. It's kind of nice because you have the original data set online, so it's hard to go wrong. Okay, now here's an important thing. For the program that I'm going to show you how to use is called JASP. Your data has to be saved in CSV format. So for this, I'm going to save as on my desktop. I'm going to call this engagement data 2. And I'm going to save it as CSV. Yes, I'm going to do it. Warning, I want to keep using that format, yes. Now this is CSV, and then before I input, I'm going to delete this first column or the actual questions out of there so that it's nothing but data. Alright, let me kick this out. Okay. In Google, to get the program, just type in JSP, probably come up with ASP statistics. Click OK. JASP, a fresh way to do statistics. If you click the download button, Chrome gets me an error. I guess it's not secure, didn't like that. I just had to work my way through that. And I get to the download page. I click download for Microsoft Windows. It's going to download the file. Double click it to execute it, and it will install it onto your computer. It doesn't take a lot of resources. I've pre-done that, so I'm going to show you the program once it gets installed. When you install it, you can open the program up. It's very streamlined, very simple. Really allows us to focus on the limited analysis that we're doing in this class without the complexity of SPSS, which I think is great. It's free so that you can do it as an employee, an internal consultant inside your organization. You can do this analysis without any cost. It's very simple. Okay. Just do File, Open, and I'm going to open first. Actually, I'm going to open my engagement 2. Here's that data. I click Open, and now my data is inside this JASP. Looks pretty good, too. All right, going back to this. That was step 8. Import your data into SPSS or JASP. If you're using SPSS, you have to do one more step, and that is to make sure that your data came in numerically as opposed to text. Sometimes SPSS will input 29 of your 30 fields as numbers and 1 of your 30 as text. Who knows why? All you have to do is toggle the number field in SPSS to let it know that it's a number, not a string. All right, any questions? That's steps 1 through 9. That's prepping your data. Okay, step 10 is your descriptive analysis. Really, the only descriptors that you're going to have is your total sample size. So you can actually do descriptive statistics. And let's just do English 1. I'm just going to do one question for this. This shows you that for question 1 of engagement, you have 58 valid responses, no missing responses, a mean of 1.655. Here's your standard deviation, and the range is 1 to 5. Now this is important for a few different reasons. One, make sure that your scale is correct. You know that you're using a 5-point Likert scale. We've done all this electronically, so there's not a whole lot of potential for error here. But if you do paper surveys sometimes, for example, and you're inputting the data from the paper survey into Excel, this is an easy way to catch errors without having to look through the whole spreadsheet. You just run your statistics on your questions. It can very quickly show you that you have something wrong with your scale. There's some outlier, something's happening. You can do more than one analysis at a time. You can do all of these. And it'll show you everything immediately across the top on your scales. Now I'm going to have you run your descriptives again after we collapse our scales. So let's come back to this.
You have one wrong.
What's that?
Go to 7. Or just somebody got to 2 to 5.
Okay, so the maximum is 4. It's possible that people just didn't answer any higher than 4 in that scale. Okay. Really, where an error would be is if you saw like a 7 down there, or a 6 or a 7. Okay, so the range is actually low, and you see that the mean is actually lower than any of the other ones, also indicating there's a tighter range of answers that people gave on question 7. Standard deviation is lower as well. It's actually the lowest variance of all the questions. Okay, so moving back up, we can get rid of all this stuff here. Go to our assignment. And you can play around with that, but really the descriptives, the sample size, I want you to do that for each variable. And I have to show you how to collapse your variables, which I'll just show you right now. So you're going to have a sample size for each variable. And maybe you can also talk about the mean and the standard deviation for each variable as well. That would be helpful. All right, now, before we collapse our variables, let me just back up. You know that each of our scales is comprised of multiple questions. So in engagement, we have a total of 9 questions. Remember when we talked about reliability, and we said that in order to justify the reliability of our analysis, the questions given a bullseye have to pretty much lump together into a tight formation. Okay? Reliability analysis is going to statistically determine if our responses, all of our questions, are in fact lumping tightly together. If they are, if they pass our minimum threshold, we can then take all of the answers to those questions for each individual and combine it into an average. Okay? So I can take the 8 questions, or 9 questions of engagement from the first individual and just come up with an average engagement score based on that individual's responses to those 9 questions. So everybody understand that?
Wait, are you collapsing them horizontal, like by the person?
Yes.
So by the individual, and then you'll take an average of all the responses?
We don't care about average of all responses. We just want the average of the individual.
So that's that person's one engagement score?
Yes.
Okay.
And we're going to match that person's 1 engagement score with their 1 satisfaction score, with their 1 turnover score. Okay, so we're always matching individual observations with the person who has answered the question. And that's what we're going to be plotting on our graphs.
You call that collapsing?
Collapse, yes. All right, now, in order to test engagement, to test whether or not our data is reliable, we have to do what's known as a reliability analysis. And that's found in descriptors. In fact, it's one of the only other choices. I love this program. So we're going to do a reliability analysis, and we're going to start with our engagement questions. And I'm going to show you questions 1 through 8 here. And we know that question 8 needs to be reversed. Okay? So I'm going to show you what reliability looks like if I fail to reverse the question and use the wrong set of answers. I put those in there. It calculates my reliability. And my Chromback alpha is hard for you to see, but that number is 0.807. Okay? That actually meets our threshold. Our threshold is 0.8. We want to see a reliability of 0.8 or higher. What's interesting, though, is that if you check this box here, Chromback alpha is item dropped, it runs a subsequent analysis that tells you what your reliability would be if you took one of your questions out. And if we look down this chart, we see that if I took this question 8 out, the reliability would jump up to 0.87. So it would be even tighter in its grouping. And that's what I want. Okay? So in this case, it's not as drastic because we still got 0.8 with that question in error. But let me take question 8 out and put my reversed question 8 in. And now my reliability actually increases. Okay? It's not going to be perfect, it's estimated. But including question 8 now, reversed, we get a reliability of 0.82. If I were to just totally omit question 8, my reliability will in fact be 0.87, which is what the analysis indicated if I were to completely omit question 8. Okay. So in order to collapse your scale, you first run a reliability analysis, and you want to make sure that all of your items in your scale combined has a Chromback alpha, which is a reliability statistic of 0.8 or higher.
What if it doesn't?
If it doesn't, then you look at what questions might be dragging that down.
Okay.
And sometimes it's 1 or 2 questions. We've asked lots of questions, so we have room to remove questions out of the analysis and still get reliability. The goal is to have a collapsed scale comprised of 2 or more questions, 2 or more items. In a lot of cases, we we have 6, 7, 8 items, so we can remove lots of questions if necessary to get that reliability to where it needs to be. Let's do work conditions. I didn't check the reverse items on that. So I'm going to run reliability on work conditions. And here's a great example. So with all 3 work conditions questions involved, my reliability is only 0.72. That's not high enough. But because I checked this box, well, what happens if I drop a question? I see that if I drop question 2, my reliability would actually be 0.85. That tells me that question 2 is probably reversed. So if I go back to my original data and I look at question 2, I'm going to look at question 1 first. I'm satisfied with my benefits package. Yes, absolutely, 1. I enjoy discussing my organization with outside people. Would I answer a 1 on that, a 5 on that? Is that related to my benefits? Maybe not. Maybe that question isn't related to my work conditions at all, and I can just delete that question out of my analysis and only collapse my items with questions 1 and 3. Okay?
Yeah, because all your friends are unemployed, you wouldn't talk about how awesome your benefits.
Yeah, exactly, right. So that question made it into my survey, but maybe it's not related to the construct I'm actually trying to measure.
I'm with that argument. So if we drop any of these, none of them get over the 0.8.
If you drop any of them?
Yeah, looking at all of it. The highest one is 0.6.
Okay, so what you have to do is you have to drop the lowest one and run it again and see if it gets you over. Okay? Because you can't look at the total list one time. You have to drop the most egregious, run it again. I hate my voice, I'm sorry. It's like, gosh, would you please clear your throat? Seriously, there's nothing there. Can't talk. All right, other questions about this?
Yeah, how do we do a proxy?
Okay, I'll have to talk to you all about that.
Okay.
Individual. All right, don't get on that. Okay, so what I want you to do in all of your variables, I want you to run this analysis I'm showing you, the reliability analysis, and I want you to record your Cronbach alpha. And I want you to record your final Cronbach alpha. So after you drop questions, after you reverse your questions, figure out what your Cronbach alpha is at that point. Once you get your final Cronbach alpha, then you have to average the relevant items into an average. So I'll show you. I'll do that in Excel. It's easiest to do. So I'm going to do constitution, or work condition rather. I'm going to call this work condition, I don't know, some denotion that this is the one I want to use. I'll just call it X. And this is going to be a function of, I know I'm not using work condition 1, I'm just going to delete that. So work condition will just simply be an average of work condition 1 and work condition 3. Or you can go like that and bring it all the way down. So now I have a variable called work condition X, or maybe you might call it work condition final. You know, some denotion that that's going to be the variable that you're actually using in your analysis. And I'm going to just create one with engagement 1 through 7.
So that's what you're talking about when you're saying you'll have an average score per person per.
Yes, this is an average per person per construct. So that's my average engagement for that individual. And I copy that down, and it gives me an average engagement for every individual. And so now I can compare average engagement individual 1 with their average work conditions. So I can test the hypothesis of work conditions influence engagement given the fact that I have these average now. you want to save this file again as a CVS. No, CSV, CVS. Full labels. CSV, engagement data. I'm going to just call this engagement data 3. Save.
So the purpose of the JASP application is truly to prove that your data is measuring what you want it to measure before you use that data to gain your averages to do your relationships.
Yes. So you're going to be bouncing back and forth between Excel and JASP as you're running these statistical analyses. Because the first part of your analysis is just preparing your data. We have to collapse our scales, and before we collapse our scales, we have to show that, in fact, this data is reliable, it's hanging tightly together, so I can justify the statistical collapsing or finding the average of these individuals' scores.
So, for one of our questions we used where you answered multiple and you put down multiple answers. Does that throw it off then when you're putting it in since there's multiple numbers?
So are you in the training group?
Yes.
Yeah, I need to talk with you guys individually.
We
Because-
had millennial, we had generation.
Okay, so that's going to be a little bit different analysis. I have to talk to you about that as well. Right now, I'm just talking about regression analysis, but you're going to have at least one variable that has a t-test, and you all are going to have just a little bit of tweaking as well, and I'll show you how to do that. For the training group, you won't have to collapse those variables. And for your millennial question, you won't have to as well. Okay? All right, so just going through the most common cases that most people are going to experience, and then we'll do special cases in a little bit. I'll probably work with the groups individually to show you that. All right, so I'm back and forth, back and forth. I finally got a final data file, hypothetically. Okay. All right, so I've done my reliability analysis for each variable. For some variables, if it's categorical, so for example, millennial question, that's not going to have reliability. For the proxy questions, it's not going to have reliability for your groups. So just say NA in those variables, I don't know what that means. I'm going to know your data as much as you do. Okay, now I want you to create a correlation table. Okay. Let's see if we... Okay, so to create a correlation matrix in this program, it's in the regression category, which is where we're going to spend our time. The request is correlation matrix. Okay, so waiting for my inputs. And here, oh, I have to put in the file. Okay, I input this new file, and now I should have my X variables in here. Okay, and I do. Here's my combined work condition and my combined engagement. Okay, to run a regression analysis, and you want to do this after you have all 6 of your variables already formatted and combined into individual variables. You run regression, correlation, and then you choose your top variables. Now, they make it easy for you. This ruler here indicates that it is a collapsed scale. So the program already knows that you have collapsed it and that you now want to utilize those actual variables in your analysis. Now I only have 2 variables here, but you're going to have 6 or so in your correlation matrix. You just bring it right over, okay, and it creates a correlation table for you. This table is kind of weak. Let me give you some more just to give you an idea. Okay. When you have more variables in there, this is what your correlation table is going to look like. And you can just copy and paste this. This is one of the things that I want you to include in your report. So you just copy, and then you can paste into Word. So that's step 13, create a correlation matrix. And once I show you how to test the hypothesis, I've pretty much given you the overview of how to engage in this process. The last step would just be interpretation, which we'll go through, and then I'll work individually in groups. Okay. So any questions on correlation table? Everybody got that? All right, let's test our first hypothesis. And we're only going to test hypothesis 1 here. And in this group, I'm looking at work conditions and engagement. So what is my dependent variable in your opinion?
Work conditions?
Well, what can fluctuate on its own irregardless of the other variable? Okay, engagement is based on work conditions. So which one would be the IV and the DV?
IV.
Yes. Engagement is the dependent variable. What we're looking at is how do work conditions impact the employee's engagement. So my dependent variable is engagement. And my independent variable here are work conditions. And I just typed that out just so that when I look at your data analysis, I know you understand the difference between dependent and independent in your analysis. And now I'm going to test this hypothesis with a regression. And I'm just going to use a linear regression analysis, which is the second selection. Remember, I've been talking about the linear equation. We've been talking about regression, so we're using linear regression. Okay. First thing it's going to ask me is, what's my dependent variable? Well, my dependent variable is engagement. Don't worry about all of that. What is going to be the covariant for my independent variable? My covariant is work conditions. That's what I'm looking at. Okay. And it actually tests the model right down here. And the output is fairly similar to SPSS. So the first thing I want to do is I want to say, is this relationship significant? So can somebody tell me, what am I looking for conceptually? You test significance. I'm looking for the p-value, right? And the p-value is found in the model, or it's listed analysis of variance, or ANOVA. Okay, and that p-value is most clearly shown right here. It's also the same as this p-value down here. They're exactly the same, but this is easier to see. So my p-value is 0.002. Is my model significant?
Yes.
Yes. Yes, it is. So that's the first thing I need to know.
So we copy and paste that? Oh, no, you just answered.
So the significance of my model, p equals 0.002. Okay? And then you might say significant. Okay, my unstandardized regression coefficient. Okay. Here's a chart is called coefficients, and they have unstandardized and standardized. We're going for unstandardized, right? And you want to make sure that you're not looking at the intercept. Don't worry about that. That's your y. That's your y-intercept. Okay. What you want to look at is the actual independent variable, which is work condition, and we see that the unstandardized coefficient is 0.25. The beta is 0.25. Okay. So I know that for every one change in work condition, what's going to happen to engagement? It's going to be a quarter change in engagement. Okay? So that's what the beta tells me. Okay, so and it's also story. So my rise over run is going to be 0.25. Finally, my R squared is 0.162. Who can tell me what that means conceptually? R squared is 0.16.
So it's not a very good predictor.
That's all right. It depends on what the other predictors are looking like. But 16% of what?
Of fluctuation and
I don't know.
Dependent variable. Dependent variable. It's always going to be your dependent variable. So 16% of my fluctuation in what? Engagement is explained by what? Work conditions, exactly. All right, so 16% of the fluctuation or variance in engagement is explained by the perception of work conditions that the employees have. And that's it. That's the test of your hypothesis. And if, in fact, that was hypothesis 1 for that group, that hypothesis would be supported.
Is that not a very high number, though?
It can be. I mean, 16% can be robust. It depends on your model, what other predictors look like. I know in some of our examples it was like 70, 80%. You probably won't see that in real life. In real life, 30 is considered 30%. Like, wow, that's like a third of the variance.
So then you test all of your independent variables against engagement, and you would focus on which ones have the highest square is the ones that you would attack first. Right?
Correct. But in our models, for our purposes, we're only going to be testing two different independent variables against engagement. When it comes to here, you're only testing this against this against this, these two against this, and this against this.
Okay.
So you don't have to worry about running any analysis like perceived work support to turnover. You don't have to run that analysis. You can, but that's not part of your model. That's just added value if you want to play around and do stuff like that. You're only testing your connected relationships. Yes, 6 hypotheses. Okay. Once you have your dependent variable listed here, once you know the significance, once you know the slope, and once you know the variance explained, you move on to the very next hypothesis. Or actually, you can give your interpretation and practice that, then you move on to your next hypothesis.
5.
There's 5.
5 hypotheses, 6 variables. 6 variables, 5 hypotheses. Yeah. Good. This is great. You guys are paying attention. I keep throwing these things out here, making sure that, you know, we're talking about not CVS Pharmacy, but rather common and limited file. Okay. So how might I interpret this? I might say the relationship.
You put it in output.
What's that?
Screen.
Oh, sure.
Thank you.
I might say the relationship between work conditions.
when you first acknowledge that there is a relationship.
Yes. So you can word it different ways. So I was going to say the relationship between work conditions and engagement is significant and positive. For every one change in work conditions, I expect a 0.25 change in engagement, and understanding work conditions explains 16% of total variance of engagement. You can write that in your interpretation bias. There's different ways that you can say that, but essentially that's the idea. So how that's wrong.
Duplicate words, you wrote each.
Oh, that's right. Okay. So that's your interpretation. It's a space for you to tell me what this means, what this data set actually means, and then you go on and test your hypothesis too. All right, any questions about that?
Yeah, so on the, looking at this, you only have, it goes up hypothesis 3, but we're doing 5,
Yes.
so just.
So at the very bottom, I said,
keep-
repeat this process for
Oh,
each of
and
your
it's
5
the last
hypotheses.
one.
Yes. Just copy and paste it and repeat it. Okay. If there are no questions, I will allow the groups to work together. And then I'm going to show a couple of groups, the training group and also the site contract group, some special instances based on the unique data that you have.